Well, good afternoon. Welcome to another Chem 400 lecture. My name is still Bill Miller, and I am still working on teaching Chem 400. I will say this, it is the middle of the semester, and it can begin to wear you down, Chem 400. It's a big class. Hang in there, I'm seeing lots of good work. Keep it up, keep going, and be finished with this class, whatever that looks like, A, B, or C. And keep doing the homework, keep getting those points. Maybe I am not a good cheerleader, but I am on your side and I'm cheering for you anyway. A couple of announcements. One, for Lab 5, you do have another week to do it till next week in Lab. There are two sets of error analysis calculations, A and B. If you have any questions about either of those, I covered A. I did not cover B in my intro to my pre-lab lecture. It's the same thing with slightly different errors. And if you have any questions, let me know. Lab 7 next week, you must be in lab by 15 minutes after whenever your lab starts in order to be allowed in. And I only do that because next lab, you'll be in teams of approximately 4, and we want everybody to contribute equally to those teams. So if you're Monday, please, well, you'll be there because you'll be in lecture. But if it's Wednesday, please be there at, by no later than 8:15. Later than 8:15, you may find the doors locked. The other thing about Lab 7, since there are really no chemicals, there are still some safety things to do, but all the chemicals will be in glass cylinders, so they'll be enclosed. And in order to aid us to use our eyes to observe some of the results, you do not need goggles next week. However, after that, you will need goggles, and I will not be loaning them out. So if you don't have goggles for Lab 8, 9, and 10, you'll be sent home. And I've told that to a bunch of people already. Homework 6 is due next Wednesday. Homework 7 will be due in 2 Wednesdays. And don't pick it up now, but homework 7 is here. If you look at the front page of homework 7, it says, note, problem number 21. Is there a problem 21? I may have changed the number. It is problem 11 now. But problem number 11 is 10 points, separate from the rest of homework. So it's one other thing. Stephen, I found some of your papers.
Oh.
They're in my office. We'll pick them up after class. I meant to tell you. Okay, so without further ado, are there any questions before we get started and picking up where we left off? Okay. Well, we'll finish up chapter 6 today. That gives you a week to do the homework after lecture, more or less. And then we'll start on chapter 7 and homework 7 material. So where we left off, energy is a product in this reaction. We said that we will refer to it as delta H reaction, and negative means it's exothermic. Negative means energy can be thought of as a product, and however you think of it, energy is produced in this process. And we have a reaction energy diagram that I sketched right here for you last time. And as far as potential energy goes, the point of this diagram is to remind you that when delta H is negative by whatever value, the potential energy of the reactants is higher than the potential energy of the products. And in very much the same way that this pen will spontaneously lower its potential energy, these products will, if, there are some stipulations, but they want to lower their energy and become products. So as we go to the next slide, why does a chemical reaction tend to occur? I will say a couple things about this. First off, chemical reactions tend to occur when they lower the potential energy of the system. Reactions tend to occur when they lower the potential energy of the system. And what we've said is that the system is usually is for us the reaction. So the reaction. And this is true for exothermic reactions. So exothermic reactions tend to occur. This is true of exothermic reactions. Therefore, exothermic reactions tend to occur. This is true of exothermic reactions. Exothermic reactions tend to occur. Bodhi, question?
Do endothermic reactions raise the potential energy?
Question, do endothermic reactions raise the potential energy? Yes.
Every time?
Every time, by definition. So, and we've drawn a couple of reaction energy diagrams for endothermic. And the difference here is for endothermic, and I think I did on this page for you last time. Endothermic reaction energy diagrams look like that. Yeah. Now, perhaps your next question is, can endothermic reactions occur? And the answer is yes. They tend not to occur, but there's more going on. And for the answer to that in depth, you really have to take Chemistry 401. But I will say that it involves something called entropy. And if entropy, which is akin to disorder, if disorder increases, that can make things occur as well. So it's more complicated. That's why I have the word tend here. Tend, so being an exothermic reaction tends to make it occur. There are other things going on as well. Okay? But the vast majority of reactions that occur are exothermic. Bodhi?
After an endothermic reaction occurs because the potential energy is higher, does it all very quickly have exothermic reaction right after?
Good question. So how perhaps the broader issue is, how does an endothermic reaction occur? One of the ways an endothermic reaction can occur is, if you think of Hess's law, reactions can be coupled, meaning you can have an overall process that is exothermic. And actually in biology, this is very often what happens. And it's not a biology class. It's been a very long time since I've taken one. However, when you turn ATP into ADP, that's an exothermic process, and you can couple that through redox reactions with endothermic processes and make the overall process occur. That's part of the story. The other way to do it is if you take a process that's endothermic and yet it increases the disorder of the system, that can make it spontaneous too. But that's beyond the scope of this class. Your take-home message for today is, all other things being equal, exothermic reactions tend to occur because they lower the potential energy of the system in the same way as I lower the potential energy of this pen when I drop it. I know, it's not a perfect answer, but in Chem 400, we're going for things that are greater than 90% true, and that's what happens, right? The endothermic reactions that occur are the less than 10%. Good. Any other questions about that, though? That's one of the like, aside from there are 3 different ways to determine delta H reaction, this is one of the take-home messages for chapter 6. Why do reactions occur? They tend to occur because they lower the energy of the potential energy of the system. Okay, well, if there are no questions, then we'll move on and talk about the last thing in chapter 6. delta H reaction in stoichiometry. We haven't done any of these calculations. I did talk in a previous lecture about how to do unit conversion factors based on this. And if you remember what I said was given a reaction with a delta H value, first you know this is negative, so you know that heat can be considered a product. Second, what that means is you can put plus 2,044 kilojoules right in the reaction, and based on that you can make your conversion factors. Your conversion factors here would be 2,044 kilojoules, and I'm going to put my minus sign back in. Per mole of C3H8. The minus sign, and I've said this a few times individually, but I want to make sure I say it for the class. The minus sign means that energy is given off or produced. Lost, yes. Lost from the system to the surroundings would be another way of putting it. Now, I also said that this number could be paired with 3 moles of CO2. And it's at this point that, as we do the discussion this week, I want to talk about the 1 coefficient. This delta H value is minus 2,044 kilojoules per mole of thing with 1 coefficient. Per mole of thing with 1 coefficient. Thing, I know, pretty sciencey, but mole of thing with mole of chemical species would be another way of saying that.
Count.
What's that?
Count.
I'm not.
Per count
Here's what I'll say about this though is when you do these kinds of conversions and when you use this this coffee cup calorimeter type equation, it is best to have the moles reacted or produced of something with a 1 coefficient. And this comes up on the discussion this week, or has already come up for the Monday discussion. But I just wanted to throw this out there. It's not necessarily needed for this problem, but it comes up. And what you will see is that on your second exam, almost everything will have a 1 coefficient and be the straightforward type of problems that you're looking for on the exam. However, if I want to challenge you, which of course I do at some points, I can put a non-1 coefficient and ask you to make sure you figure it out. Like that's the next level of understanding. And so know how to do all the stuff that we've been doing. And in lab this week, everything had a 1 coefficient. That's the basic level of understanding. The more advanced level would be, how do I deal with non-1 coefficients when I have them? And that's why I'm going over it right now. And it's tricky. And I know that I'm not teaching it in a way that everybody can understand it, but I don't know how to. I think we just have to work it out, you, me, and figure it out. So I don't know. Okay, so now back to the actual problem that we're solving here. This one says, when 51.2 liters of oxygen at 1 atmosphere and 298 Kelvin are consumed in the burning of propane, how much heat energy is produced? Heat energy just to reiterate, this is a Q and is related to delta H of reaction. So Qs, as we've seen in lab, have units of joules. Or kilojoules, but just energy. Delta H has units of joules or kilojoules per mole or per gram. That's how you tell them apart. And I will say this, if you go to Khan Academy, I think they do it the same, but there are places that have different ways of dealing with the units. So just be aware of that. Okay, well, I have oxygen gas. It is a gas. I have volume, I have pressure, and I have temperature. I can find moles of that gas using the ideal gas law. PV equals nRT. And when I do this, I will solve for N. I will personalize it first for oxygen, because I will have a pressure of oxygen. I will solve for my moles of oxygen and plug everything in. I get 2.09 moles. Of oxygen, and that's probably a good number. I mean, it is a good number, but I look at, I'm at 1 atmosphere, pretty close to STP for my temperature as well. And so, since 1 mole of gas at STP is 22.4 liters, that's the molar volume, we should be a little bit more than 2. I don't know, I just like to check in and see if my answer makes sense from what I know from my gas. Now to finish this problem, I have my moles of O2. I can create a conversion factor from my moles and my energy. And that conversion factor says there's negative 2,044 kilojoules per 5 moles of O2. My moles cancel out. Alicia, question?
When the problem is stated, it says delta H. It doesn't specify STP with O2 or?
That's right. So the problem doesn't specify. So all this will be how you get it.
Right.
The minus 2,044 kilojoules per mole. Your interpretation of that is that's minus 2,044 kilojoules per mole of, in this case, propane. And for me, I mean, my way of dealing with it is putting it in the equation, putting it in the reaction, and then treating it like a coefficient. What I mean by that is that I could do 3 to 4 for a mole ratio of these two, or I could do 5 to 2,044 for the energy. So you're right, it doesn't tell you that? Well, no, but that's the convention, and so we want to get you used to it. How do you think about these problems given how you will typically, like if you go to a bio class and they tell you a delta H reaction because they're interested in how exothermic a process is, that's how you'll see it. So, does that answer your question? Sort of? Okay. Stephen?
So does that mean that, so since the negative 2,044 kilojoules is for 1 mole of propane, essentially, right?
Yep.
So that means that what we're looking for is that's why it's oxygen, because we're looking for the opposite of that, because we already know that that's a 1-1.
Right.
Okay.
So we don't, and you could actually do this to propane, and then propane to oxygen.
You're doing it just a different way for the same outcome.
Yes, yeah. So like there's multiple ways to get to this factor, and you should be ready to get there, is what I'm saying.
Because that's going to give you the entirety of the reaction. We're looking for how much each mole of oxygen produces. Right?
Yep.
Okay.
Yeah. Any other questions? All right. Then my moles cancel. I'm left with units of kilojoules, negative 854. Kilojoules, depending upon the time over which that propane is burned, that might be enough to grill my Impossible Burger. But that's an energy, and that energy can be used for something else. And it does say how much heat energy is produced. That tells you that we should have units of joules or kilojoules down there. For the same reaction, how much energy is produced when 16.4 grams of propane are burned? I'm going to consider this a companion problem. So the answer should be online already on the Chem for Wonder website. If not, I think it is. Let me know. Let's see what the next slide is. Oh, yes. Let's go ahead and do this one. This problem, as far as chapter 6 goes, might be what I would consider a bread and butter problem. Bread and butter problems mean the basic stuff that you gotta have down in order to be ready for exam number 2. That's why we're gonna do it. It says calculate heat released for decomposing 10.0 grams of limestone calcium carbonate. And this problem pairs two different things. One is you have to take the delta HF values, calculate delta H reaction for this reaction, and then use that delta H reaction, just like we did back here, to figure out how much heat is released. So it is a two-step problem, but I still consider it bread and butter. The process goes like this. To find delta H reaction, I write out my delta HF values. Right, and what you would probably have to do on an exam is go to that sheet that has all of these and look each of these up. I have calcium carbonate minus 1207.6. Calcium oxide and oxygen. To calculate delta H reaction, and this will be a standard state value because we are using standard state values from the table. It is products minus reactants. Minus whatever the reactants are. Where the oxygen's minus 0, I still put it in there. If you remember when I did this problem before, I multiplied times the coefficients. I'm still doing that, except they're all ones this time, so I just choose not to write them. Coefficients are always multiplied by these numbers. A negative negative here, that becomes a positive. That's positive 1207. That means that this delta H will be positive overall when I do the math. My delta H reaction, 572.7. Kilojoules per mole, that's a positive number. That means this is an endothermic process. Then why does the problem say heat released? That would be my question. Wait a minute. Did I do this right?
Is the 0 supposed to be on the right side?
Oh, yeah. Thank you. I don't know why I cannot get my products and my reactants right for this.
It should be negative.
It should be 107
All right.
plus.
No, come on.
Deep breath. Let me revisit this. All right, so it should be products. Let me write it out nicely. Products minus reactants and yes, this is the right number. It should say calculate the heat absorbed, needed, taken in, as we become an endothermic thesaurus at that point, and give other words, although I don't know what they would be. Does that look better? Thank you, Brenda. Does that? Then, this is kilojoules per mole. We know we have 10 grams of limestone. We convert that into moles, and then it is 572.7 kilojoules per my 1 mole. Molar mass of calcium carbonate, 100.09 grams. And this conversion factor here does match our delta H when it's referring to the thing with the 1 coefficient, so it fits perfect. Multiply this out, divide as necessary, you should get 57.2 kilojoules needed. Bread and butter.
Per mole.
Not per mole. Our units of moles cancel out. We all know how much I love canceling units. We also know
We have them out there.
that it just is heat needed. And if I'm asking for a heat, it should be just in kilojoules. Or joules, or units of energy. In theory, we don't talk very much about it, but the only other thing I could throw at you would be units of calories. They're also energy. Probably won't see them, not on the exam, maybe on the homework. Any other questions? All right. And so what you'll see on homework number 6, if you haven't already, is that because there are a few different types of problems, I tend to tell you what problem type it is. Like coffee cup calorimetry problem with 2 materials, coffee cup calorimetry problem with a reaction. Calculate delta H reaction from delta HF values. So you start to learn how to identify each type of problem. With that, I think that's the end of chapter 6. In fact, I'll advance the slide carousel here. That's the end. So let me pull up chapter 7. Take me a minute. Take me 2 minutes. There we go. CHEM 400 is nothing if not a hodgepodge of topics that introduce the concepts useful in chemistry. We just talked about heat energy and called it thermochemistry. Now we're going to talk about the nature of light, and we're going to end up talking in Chapter 7 about the quantum mechanical model of the atom. But first we talk about light. And the first thing we need to know about light is that light is a form of electromagnetic radiation composed of perpendicular oscillating waves, one for the electric field, that's what goes in this line, one for the magnetic field. And I have a picture of those here. And what it amounts to is these two waves are orthogonal to each other. Does anybody know what orthogonal means? Or can give a definition of it? How about the term perpendicular? What does perpendicular mean? At 90 degrees to each other, right? Okay. Well, orthogonal is the same thing instead of for lines, for planes. So if I have a plane and I have another plane that is orthogonal to it, it is 90 degrees to it and a surface. Okay? Now, how that comes into play here is the electric field component will be a wave, and let's say it's a wave going up and down. The magnetic field, and so it's in this plane going up and down. The magnetic field will be orthogonal to it, left to right. And so the magnetic field will go like this. And both of those waves are in directions that are, well, let's say this. Allow me to demonstrate. The wave is traveling that way. And the electric field goes like this, and the magnetic field goes like this. And together,
They cross at the same time.
in the easiest picture of it, they cross at the same time. It can be more complicated than that. But this is the simplest way to picture it. Okay? And so you're thinking of the motion of these waves as far as how high they're going. One's going up in this and they're traveling in these directions like this. And what we need to know from this is, first of all, that's where the term electromagnetic radiation comes from. It has electric and magnetic field properties. And they will interact with electric and magnetic fields of other materials. And we don't really deal at all with the magnetic field nature of it. We deal with the electric field a little bit, because the electric field of light waves will interact with electrons, as we will see. Anyway, there are two aspects to this, but from now on and for the rest of the class, I will just draw the wave like this. And we will ignore the orthogonal magnetic field. And it doesn't really come up, but it's broadly useful to know that. Any questions about that? So now, after this slide, waves come up as just as if they only had the electric field. All right. Now, electromagnetic radiation, waves move through space at the same constant speed. That is called the speed of light. Its symbol is lowercase c. And for us, we will use the constant value 3.00 times 10 to the 8th meters per second. Bodhi, question?
Is it always that speed?
Is it always that speed? Only in a vacuum. Yes, only in a vacuum. Speed of light in a vacuum.
So, in real life, it varies? That speed of light? It speeds up and slows down?
Does the speed of light vary in real materials? Yes. And is slower than that. Think of that as the maximum. And the reason it slows down in materials is it interacts with those materials. And so, and one example of that is if you've ever seen a spoon in a glass of water. So the spoon, that's not in our class.
Diffraction or refraction?
The spoon appears to bend as it goes from the water to the air. That is refraction as the speed of light in the two materials changes. Question, Bodhi?
So does that mean, like, so say for example, the light coming from the sun is going that fast until it interacts with, like, say, the atmosphere, and then it slows down?
It does slow down, and it bends. Yes.
So, but when it's going through space to get to the Earth, it's going that fast?
Since space is essentially a vacuum, that's the speed. Now, that's very, the other thing I want to say is it's called the speed of light, but a better description of it is the speed of electromagnetic radiation. Because we will see that in a vacuum, visible light, ultraviolet, infrared, X-rays, every single type of electromagnetic radiation goes at this speed. So I'm going to write over here, speed of electromagnetic radiation. In a vacuum. Okay. Now that's very different than the speed of sound. So as you hear my voice, do you know how you hear my voice? Is it electromagnetic radiation? I know it appears to be, but is it electromagnetic radiation that is traveling to your ears?
No.
What is it? Vibrations of oxygen, but really all of the air. That's how sound propagates. So sound is propagating that way. And that is a very different speed, 340 meters per second, because that is a physical process of vibrations and travel. So anyway, different process. The picture here, I know this is the West Coast, but does anybody know what this is called? Lightning, thank you. They have this on the East Coast, where I'm moving. And lately they've had it here, haven't they? More and more. I mean, it's scary out here when it happens in the summertime because of potential fires. But it seems like it's happening more and more. But the idea is that you can tell how far away lightning is based on when the lightning appears to your eyes and when you hear the thunder of the vibrations. And it's approximately, I think, supposed to be a second a mile that it is away. 5 seconds per mile? Yeah. And I always thought it was much farther away, which maybe is good. Probably not. Yeah, so anyway, just different speeds for the different ways in which waves can propagate is the only point I'm making now. And everything we do will deal with electromagnetic radiation in this class. There we go. Now, in order to characterize our waves, we will need two different properties of them. The wavelength, which is the distance from peak to peak, and the amplitude. The amplitude will be involved with the magnitude or intensity of the wave. And we'll talk more about this later. What we are going to talk about a lot now is the wavelength. And the frequency. And for electromagnetic radiation, the wavelength and the frequency are not independent, they are related. By the speed of light. So c is the speed of light. It is equal to lambda, the lowercase Greek letter lambda, which looks like this when I draw it, times frequency, and I draw the frequency as sort of a V with a hat on the back of it. A slightly blocky. And frequency is at once the simplest thing to think about and the most complex, at least in my opinion. And so frequency really does just mean how frequently something occurs. For example, how frequently do you see me? And don't say way too often. That is not a specific enough frequency. You could say, depending upon if you come to office hours or not, if you only see me on Mondays and Wednesdays, then your frequency of seeing me would be 2 times per week. Because frequencies have units of per time. How frequently is something happening? If you come to office hours, it might be 3 times or 4 times per week. And for frequency of electromagnetic waves, it's the number of waves that pass a point in a given period of time. And it just turns out to be a much larger number. As another example of frequency, do you know what the frequency of electricity is in the walls of this building? 60 hertz. Hertz, and I'll write that out too. But what does hertz mean?
Per second. Cycles per second.
Per second, and the cycles is taken, I don't know if it shows up necessarily in units, but 1 hertz equals 1 second to the minus 1, or 1 per second. The seconds to the minus 1 means that seconds is in the denominator, which is equivalent to what I've drawn here. And I'm a big fan, in general, of 1/2 units, because I'm familiar with seconds and what they are. We'll see some numbers reported in hertz. I think people in general prefer not to have things in the denominator for their units, and so I think that's why they evolved to hertz. I don't know. You'll see both of them, but I will tend to immediately convert them into per seconds. Per seconds the most. So, and it just means how often do things happen. So, if this were the wave of electricity that's in the walls of this building, and I was to stick my finger right here, and the electricity in the wire would go past my finger 60 times per second. So another example of frequency. Now, and we'll do some examples in a couple minutes, but now let's talk about energy. And we'll get into more specific examples in a couple minutes, but the total energy is proportional to the amplitude of the waves and the frequency. Without using numbers, the larger amplitude will mean larger amounts of energy. And higher frequency will mean larger amounts of energy. Now let's come back to this equation for a minute. If C is a constant, which is the speed of electromagnetic radiation, speed of light if you will, then if frequency goes higher, what happens to wavelength?
Gets lower.
Wavelength gets lower. So C here, we'll say lower or shorter wavelength equals larger amounts or higher amounts of energy. Maybe, I don't know, would higher be a better word here? It's not an English class. I'm going to go with higher. And then for lower wavelength, I will also write equals higher amounts of energy. Because, since they're on the same side of the equation, wavelength and frequency are inversely related. Any questions about this? Wavelength and frequency are related by the speed of light. I'm going to write the same equation right here. Speed of light equals wavelength times frequency. Frequency is in seconds to the -1. Wavelength is in meters. Speed of light in meters per second. Good. Now let's talk about the electromagnetic spectrum. Is yours in color? No. I decided to save you 50 cents and not on the price of the book and not do color this time. So you have to imagine the lovely colors here. Here's the visible portion of the spectrum. And it is but a tiny portion of the electromagnetic spectrum. We've got frequency here. We've got wavelength here. The frequencies of visible light are right around 10 to the 14 or 10 to the 15. Those are positive numbers. Seconds to the -1. That means if I hold my finger up and I think of the waves of light that are going past it as they come in from the beautiful day outside, then each of those waves is passing my finger 10 to the 14 times per second. So very fast. Same thing as far as wavelength. Looks like we're down in here around the 10 to the minus 6, 10 to the minus, or 10 to the minus 6 range in meters. And then down here we've got nanometers for the wavelengths. We'll oftentimes refer to nanometers. And I would say in the colors of the spectrum going from red to violet, we might consider them to go by Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. Although I don't know the difference between indigo and violet myself. Things you need to know about the ultraviolet spectrum that I'm presenting right here. You need to know that approximately between 700 or 750 nanometers is approximately where red is. And that is the edge of the visible spectrum. The other edge is around 400 nanometers. And you have to know that violet has the shortest wavelength and the highest energy. Of the colors in the visible region. For example, and then I'll take your question or comment. So, which color has a higher energy, orange or red? Higher energy, orange does. That's the type of question I can ask you. I won't ask you which specific wavelengths they have. But I do want you to know the relative order of them. Alicia, you had a question?
It's weird how violet and red look so much more like one another. You always have like a circle, not a circle.
Well, so I think, Alicia, if you're referring to the color wheel, there is a circle of colors. And we do talk about the color wheel at the end of Chem 400. And you talk when I teach Chem 401, there's a whole section on the color wheel. Because the thing about the colors is that while this is the order of the wavelengths and frequencies and energies, how we view colors depends on, there is a color wheel, a circle of color. So, anyway, but that's Chem 401 stuff for now. There is no circle of colors, of life, of anything in Chem 400. Odie?
Where would white and black be?
Where would white and black be? So white will be all of these overlapping, and black will be all of these taken away or absorbed. And we're talking about that coming up. White light is the overlap of all of these colors. And there's actually, so my wife, she's a graphic designer, she teaches color theory, she knows way more about this stuff. There's additive colors, there's subtractive colors, there's colors when you think of how this projector projects colors versus how you print colors, and they're all related, yet slightly different. Cody?
So would white have higher energy than black?
Would white have higher energy than black? Well, since white is all of the colors and all of the visible colors overlapping, and black is all of them absent, you can think of black light, well, you can think of black as a color that does mean the absence of energy. Like when it's dark out, there's no light. And, I mean, it seems obvious, but I'm going to say it anyway. You can't get sunburnt at night because there's no energy, no light coming down on you. But you can during the day. It's not all the wavelengths that do it. It'll turn out to be the ones that are higher energy, shorter wavelength, the ultraviolet. I don't know, but so I don't know if that answers your question. But let me see if I can say a couple other things. So in addition to Roy G. Bibb and knowing the order of which one has the highest energy and the shortest wavelength, you do have to know that ultraviolet is even higher energy. And that is relatively easy to remember, I hope, because ultraviolet light is the light that burns your skin, and therefore must have higher energy. If you only are exposed to visible light, it will not burn your skin because it does not have enough energy. And later in the course, for fun, or not for fun, for exams, we do prove that the reason that ultraviolet light has enough energy is because the energy of ultraviolet light has enough energy to break bonds. And that's what happens when you get sunburned, is your skin, the bonds break, and you start to decompose. I don't know about decompose, but you do break bonds, and that's how it does damage your skin. On the other hand, infrared, lower energy than even red, and microwaves and radio waves. So cell phones, way out here, pretty low energy, not enough energy to break bonds for sure. And what I need you to know is the order of the visible, ultraviolet, and infrared, as far as what their energy, what their wavelength, and what their frequencies are relative to each other. Now believe me, we're getting to atoms, but before we get to atoms, I want you to have a firm grasp of how light works. Wave interference, the interaction between waves is called interference. When waves interact so that they add to make a larger wave, it is called constructive interference. So I'm going to write that on constructive right here. Another way of describing this is that when two waves are in phase, they create a situation where you have constructive interference. So waves in phase, and you can see it's like the heights add, and the troughs add. So you get a deeper bottom and a higher peak. And the peaks are aligned. We'll use this phrase later on in phase. When waves interact so they cancel each other, it is called destructive interference. And in this case, the trough and the peak are aligned. The trough and the peak are aligned. And for electromagnetic radiation with the same wavelength, they completely cancel in this case. And what you might imagine is, depending upon how they line up, if they're not exactly aligned either of these ways, you can create waves that are little waves, waves that are almost double, and everything in between. So these are the perfect cases of them being exactly in phase and exactly out of phase. always fun to think about. How do you draw no wave? I guess it's just a straight line. This is no wave. It's not meant to say the wave is a line.
That's how noise canceling headphones.
Sorry?
How noise canceling headphones work.
Is that how noise canceling headphones work? Yes, very nice. They produce waves, they counteract the waves that are coming in. And they do it the best they can. Do they work? I know, the only noise canceling I have is like this, so, and it's mechanical, it's not actually. I think they do work, and I love the technology that somebody applied noise canceling to. Although it's not exactly the same because they are sound waves, different than these, but they're basically trying to counteract the waves coming in. Okay, so when these waves encounter an obstacle or opening in a barrier that is about the same size as the wavelength, they bend around it. This is called diffraction. And if you've ever been at the beach and there's a barrier like this, you can actually see this happen sometimes. Or you've seen experiments in physics classes where they make waves in a trough of water. It works for water waves. It also works for light waves. And so these are the wave crests or the wave peaks. And so we might think of this as waves like this approaching here. And then as they go through, they are bent. That is diffraction. Question, Jason?
The wave won't diffract if it's larger or smaller than the wavelength?
Will the wave diffract if this spacing and this spacing are very different? Not noticeably. It has to be similar sized. Yeah. Because there is a matching effect there. I'd have to think about precisely how those work, but that is right. And so I guess if this were much larger, you would actually have a little bit of diffraction around the edges, but you wouldn't produce these nice coherent waves. And if this were much smaller, it just basically blocked them. So I guess maybe the way to put it is to get nice waves out this side, they should be approximately the same size. Okay. Good. I hadn't thought of that. That's good. Yep. Everything we've been talking about so far has been waves. Light travels as waves. This is what happens for light. If we think about light, do you remember what the wavelength of violet light was?
400
It was about 400 nanometers. What that means is that this distance is 400 nanometers, which means this distance must also be about 400 nanometers. So these are not necessarily super simple experiments to do, but if you can create holes that are about 400 nanometers, you can observe this effect. It's much easier to do with water waves, too. At least that's macroscopic. I don't know how I'm going to write that. I think I'm just going to write, this happens for light, or this happens for all electromagnetic radiation. And it is one of the pieces of evidence that light is a wave. If it's a wave, and then it will diffract. So, therefore, light is a wave. At least one piece of evidence. electromagnetic, so this happens for all electromagnetic radiation because it is all waves. I'm not sure that's the best way to put it, but true. But waves of electromagnetic radiation are not particles. If we do the same type of experiment with particles, the particles go straight through and there is no diffraction. So no diffraction. Of particles. Dot, dot, dot. And I'm going to tell you the answer, and then we'll talk about why it's true, except for electrons. And we'll bring back our abbreviation for electrons. Electrons will turn out to exhibit diffraction-like behavior, and that is why we are doing this, is because electrons are light enough and close enough to zero mass that we can observe, or we will observe their wave-like properties. Okay? Now, proton, particle, straight through. Atom, even of hydrogen, boop, straight through. It is only for electrons. And if this were a physics class, you might say, what about gluons? And I would say, first off, I'm in the wrong class because I shouldn't be teaching a physics class. But the next thing I would say is, anything that has the mass of an electron or less, yes, it will diffract. And these kinds of properties become important. So, particle behavior, protons, or let's just say proton, neutron, hydrogen, hydrogen atom, etc. And since that's the smallest atom, everything bigger than that also. Questions about that?
Doesn't a hydrogen atom have an electron?
Question, doesn't hydrogen atom have an electron? Yes.
You mean iron, hydrogen iron.
A hydrogen atom has an electron and a proton stuck together. Therefore, it is heavier than a proton. And therefore, the electron, if we were to think of it by itself, if you have an electron by itself, it does the diffraction.
Okay.
But when it's attached to a hydrogen atom, it is simplest to think of them as just permanently attached, and therefore straight through. Okay. All right, so we're getting there, and for this one, the diffraction of light through two slits separated by a distance comparable to the wavelength results in an interference pattern. Interference pattern of the diffracted waves. And this is what's called a double slit experiment because there are two slits. And we're doing this with the light right now. And as that light Well, here we go. Wavelength is this way. Yep, approximately the size of the two slits. Then what you will see on a screen is a pattern of dark and light spots. That is your interference pattern. Sometimes where there is what's called constructive interference, they will make a brighter area, and where there is destructive interference, it will be darker. Any questions about that? All right. Well, then let's keep going to a few calculations. Now, these types of calculations are Chapter 7, bread and butter type calculations, meaning we will do a lot of them, and they will be straightforward, hopefully, by the time of the exam. It says, for the relationship between frequency and wavelength, the longest wavelength of red light is wavelength equals 750 nanometers. What is its frequency? The basis equation, and this equation is given on your conversion and equation sheet. Speed of light equals wavelength times frequency. We're solving for frequency. And plugging in 3.00 times 10 to the 8. Meters per second. I've been given 750 nanometers. 1 nanometer equals 10 to the what meters? -9. Nanometers are extremely tiny things. 1 nanometer is 10 to the -9 meters. Therefore, 750 nanometers will be an extremely small amount of meters. If you do the math, you get 7.50 times 10 to the -7. Meters. And if you put this down here in the bottom, and work the math, everything will work out lovely. I have a slightly different approach to doing this. Here's my approach. I write the 750 down there, and in my head I think nanometers, and then my pen writes times 10 to the -9 meters. So I've just done this unit conversion in one step. You can always do it in 2 steps. I don't care which way you do it. Please remember that nanometers are tiny things, and when you get a tiny number here, you'll know why. Multiply this out, just thinking about this, 8 and -9, this is going to be a very large number because it's 8 divided by -9, so it's like 8 plus 9, so it's around 10 to the 17th. I know this is a hundreds number, almost 1,000, so that throws it off a bit. I've also told you once already, and you'll see this, that in the visible region, frequencies are 10 to the 14, 10 to the 15 meters per second. Seconds to the -1. And when we get 4.0 times 10 to the 14 seconds to the -1, that is typical. Well, that's red line. And I'll accept units of seconds to the -1. I'll accept units of 1/2 and I'll accept units of hertz as well. They're all equivalent to me. Any questions about this? You can tell how long ago I made up my lecture notes. It was back when 3G was popular and, in fact, new. For the 3G cell phone network, does anybody know what the frequency is? In gigahertz?
Is it 2.4 gigahertz or something like
it's around 2. I was so excited when I did this because I thought the 3G was 3 gigahertz. Lies.
Third generation or something.
Third generation. Do you know what the cell phone network's frequency is for 4G? 2 gigahertz. They're all in the same region. They have not gotten any faster. In fact, they've just figured out how to handle the signals better, and and transmit more data in the same frequency.
Isn't that because different things run at different frequencies? So like, you have Wi-Fi running the same frequencies, your cell phone, you would have interference?
You would have interference, yeah. If you had Wi-Fi, cell phones, they used to have the handheld phones in your house. Remember when people had landlines? No, I do. Anyway, gigahertz. What's a gigahertz? 1 gigahertz is how many hertz?
A billion.
A billion. Kilo, mega, giga. Yeah. So, giga means 10 to the 9th. Hertz means seconds to the -1. The question here, what is the wavelength of this electromagnetic radiation? The equation works for all types of electromagnetic radiation. No electromagnetic radiation up my sleeve. Well, we can solve for the wavelength by rearranging the equation to solve for it, and then plugging. And depending upon how you want to do it, technically, I only have 1 sig fig down there, so I should get, well, I'll carry my answer to 2 sig figs, because I can't do just 1. 0.15 in my units. My seconds, my per seconds, and my per seconds cancel. And cell phone signals are about 1/10 of a meter long. And they do vary. Some of them are 2.4, some of them are 2.3, some of them are even 1.8 gigahertz, but they're all around that 2 region. That seems like a very good place to stop for today. We'll pick up there next time. Remember, we're part of the way through Chapter 7, so you should be able to do all of Chapter 6 homework. If not, come see me. Jason, question?
Is that supposed to be 2 times 10 to the -9?
Oh, 2 to, so thank you, sorry, I got so carried away. 2 to the, thank you,
Okay.
times 10 to the not plus 9 seconds to the -1. I apologize for that.
How does that switch?